All right, we're continuing through the argument between Huygens and Newton, and I can't emphasize this enough. Christian Huygens dedicated his entire life to studying wave behavior, wave theory, and so on and so forth. Newton put very, very little effort into it. Okay, he kind of thought about it once in a while, came up with his postulations, and without any evidence whatsoever, just with an analogy, his word was being taken over Christian Huygens. So you can imagine how frustrating it was for Christian Huygens when every piece of research is disproved or discredited simply by Newton saying, no, that's not the way it works. So as we move on, we're talking about partial reflection, partial refraction, and we're going to talk about this in the property in light. If you've ever been on water or at the beach, you've had glare off the water before. So that means that some of the light waves are coming down on an angle in the water, and what they are doing, they're reflecting back into your eyes. So that's why you get glare off the water. But you also know at the same time that if you're underwater, there's still light down there. And what happens is some of the light refracts down into or underneath the surface. Okay, so easily proven, easily showed or displayed by Huygens. You can visualize it because it's exactly your beach scenario, that glare, okay, and then that refraction we've talked about. Newton postulated that, not all light particles are the same size. So we have our large particles, we have our medium-sized particles, and we have our little particles. And they all constitute or make up what we call light. So big particle, medium particle, little particle, big particle. So these particles, when they reach another medium or another surface, well, they kind of, not all of them are going to fit in. Some just don't fit into this medium. So you're going to get maybe only the little particles get through into the water, and all the large particles and medium particles are reflected. Well, that makes sense. They just don't fit. All right, so you get some bounce off, and the ones that do fit into the medium continue on their way. So light is made of different sized particles. Of different sized particles. And some just don't fit into the new medium. All right, and then this one we can prove from glare off water. All right, so that was Newton's argument right there. So at this point in time, you're kind of thinking, how is this wishy-washy stuff flying with people that are considered educated? They're just saying, oh, well, Newton says that, makes sense, has to be right, versus concrete evidence. Well, let's move on to dispersion. So dispersion is when different colors in the light spectrum bend differently. So that's when you get light entering a prism and you get a rainbow effect, just to simplify it. So we have our prism. So what Huygens said, and he had a prism, he said, listen, different color waves have different wavelengths. So each color has a different wavelength. And therefore, bends differently. So he's saying that his blue light is going to bend like that. This green light, and I only have 3 colored pens, so there we go. All right, so that color spectrum light, it's made up of different wavelengths. Each one has or bends at a different amount when it enters that prism. So Newton said, well, yeah, you're kind of right. I already told you the particles are different sizes. So the particle, we got our big ones, our little ones, our medium ones. big ones, little, medium, medium, little, little, big, little. I already told you, light is made up of different sized particles. You're just trying to steal my ideas here, Huygens. And what happens is that the little particles, they're smaller, so they bend quicker. The bigger ones, they don't bend quite as much. And then the medium ones are somewhere in between. So you're just kind of changing and making stuff up here. Obviously, different size particles get filtered. And of course, the audience goes, ah. So different size particles get filtered as they enter from one medium to the next. So again, we have empirical evidence on the left showing that the light does break apart. And I guess perhaps empirical is maybe a little strong since he couldn't actually measure the wavelength. And on the right side, we have that particle theory of different size makes a difference. Finally, in my opinion, this is where Christian Huygens was ultimately defeated, because he said that, or agreed, that waves are a transfer of energy. And then we talked about that in our grade 11 course. We then said that waves need a medium to pass the energy. Again, simplified version here. So in a vacuum, there's no medium. So if there's no medium, how does the energy get transferred? Okay, that transfer of energy, we talked about sound. Sound cannot occur inside a vacuum. Whereas Newton is sitting there and saying, oh, here's my sun, and the sun is generating a source of light. And guess what? Particles, objects don't need a medium to travel. In a vacuum, something will move. We can drop stuff, we can throw stuff in a vacuum, and they'll make it to Earth. They don't need a medium. So particles don't need a medium. So again, in my opinion, this is where Huygens was ultimately defeated in the minds of a lot of scientists. Don't need a medium. So where does that leave us? Where does that leave us indeed? Well, evolution of light. Let's talk about that. Evolution of light, Christian Huygens, he passes away. So this is after the great debates raged for a good part of Christian Huygens' career. He passes away, and so does Newton, never knowing the fact that everything he did, every theory that he constructed, was absolutely correct. Christian Huygens died without being recognized within his time. All right? So 200 CE to 1600 CE. Light is argued to be either particle or wave. And ultimately, it came down to Christian Huygens versus Sir Isaac Newton. After 1600, physicists go along with Newton. Okay? So at that point in time, it's definitive. They've made a decision. We are going with particles. Light is made up of particles, even though there's some quick hand waving and a little bit shaky on some of the concepts. But that allows them to progress. It makes progress difficult in terms of researching what's really happening. Then we have a branch of scientists that come out of it saying that, there must be a duality here, because if we assume waves for certain situations where Huygens, in our opinion, defeated Newton, the math works out. In the places where Huygens wasn't able to answer Newton or counter Newton, Newton's theories actually work. So now, how about we just assume it's both a wave and a light? And what that does is it allows for research to move forward in that field of light. And finally, ultimately what happens is James Maxwell arrives for us, and he rides to our rescue. James Maxwell, we talked about this in the previous unit, developed, or I should say created, the electromagnetic wave, or identified the electromagnetic wave. So how does the wave theory of light explain all aspects? How can we justify Huygens and his theory that light is a wave, can't pass through a medium? Well, in the previous unit, we said that if we have an electric field, so our E, and we have a magnetic field, that fluctuation or oscillation in the fields creates the other. So our electric field we have there, and again, I'm going to put lines showing that this one is the vertical axis. If you have an electric field, then that electric field will generate a magnetic field. So coming out of the page, it looks like this, and these ones are going parallel to that axis. So if we postulate that light is in fact an electromagnetic wave, then light can travel without a vacuum. So if light is an electromagnetic wave, it does not need a medium. So thanks to James Maxwell and the discovery of this electromagnetic wave, we can postulate, or we now know, that light travels as electromagnetic wave. Now there's a clause down below here, and at the end of this unit I'm going to show you some neat videos. So however, physicists still use the particle model so even though that we've now proven everything true that Huygens said, physicists still need to use the particle model sometimes to explain the behavior of light, okay, which is kind of neat when you think about it. All right, so there is a physics history lesson for you in terms of light, and it kind of gives you a feel for where light started, where it ended at, and why it was so important that we went through and did the electric and magnetic field unit prior to this. So now it's our link to light here. So everything we talked about in the previous unit, some of it's going to carry through for us, and specifically all the concepts behind the electric and magnetic field, that generation that allows it to make that connection. So moving along, at this point, again, there's no assigned homework. Probably, if I haven't already, I will be getting the lab going in class to give you something to do within that construct. So we'll be doing some investigation. So anyhow, good luck, and we'll see you in the next video.